21951 A04 F0 of branch ECEC section. In this presentation, I am going to talk about Mayer's and Norton's theorem. Mayer's theorem. In number theory, Mayer's theorem on quadratic forms states that an indefinite quadratic form Q in 5 or more variables over the field or rational numbers non-trivially represents 0. In other words, if the equation q of x is equals to 0 has a non-zero real solution, then it has a non-zero rational solution. The converse is obvious. By clearing the denominators, an integral solution x may also be found. Mayer's theorem is usually deduced from the Minkowski theorem, which was proved later, and the following statement: a rational quadratic form in 5 or more variables represents 0 over the field Qp of the p asterisk numbers for all p. Mayer's theorem is best possible with respect to the number of variables. They are indefinite rational quadratic forms Q in 4 variables which do not represent 0. One family of examples is given by Q of x1, x2, x3, x4 is equals to x1 x2 plus x22 minus p of x32 plus p of x32 plus x42, where p is a prime number that is congruent to 3 modulo 4. This can be proved by the method of infinite descent using the fact that if the sum of two perfect squares is divisible by such a p, then each summand is divisible by p. Mayer's formula. According to Mayer's relation or Mayer's formula, the difference between these two heat capacities is equal to universal gas constant. Thus, the molar specific heat at a constant pressure is equal, that is Cp is equals to Cv plus R. Julius Robert Mayer, a German chemist and physicist, derived a relation between specific heat at constant pressure and the specific heat at constant volume for an ideal gas. He studied the fact that the specific heat capacity at constant pressure Cp is slightly greater than at constant volume Cv. He reasoned that this Cp is greater than the molar specific heat at constant volume Cv because energy must now be supplied not only to raise the temperature of the gas but also for the gas to do work. Now next, Norton's theorem. In direct current DC circuit theory, Norton's theorem, also called the Mayer-Norton theorem, is a simplification that can be applied to networks made of linear time invariant resistance, voltage sources and current sources. at a pair of terminals of the network, it can be replaced by a current source and a single resistor in parallel. This is the circuit diagram. Any black box containing resistance only and voltage current sources can be replaced by an equivalent circuit consisting of an equivalent current sources in parallel connection with an equivalent resistance. Edward Laurie Norton. For alternating current AC systems, the theorem can be applied to reactive impedances as well as resistance. The Norton equivalent circuit is used to represent any network of linear sources and impedances at a given frequency. Norton's theorem and its dual, that is Thevenin's theorem, are widely used for circuit analysis simplification and to study circuits initial condition and steady state response. Norton's theorem was independently derived in 1926 by Siemens and Askey. Researcher Hans Ferdinand Mayer 1895 to 1980 and Bell Labs engineer Edward Laurie Norton 1898 to 1983. To find the equivalent, the Norton current INO is calculated as the current flowing at the terminals into a short circuit. Zero resistance between A and B. This is INO. The Norton resistance RNO is found by calculating the output voltage produced with no resistance connected at the terminals. Equivalently, this is the resistance between the terminals with all independent voltage sources short circuited and independent current sources open circuited. This is equivalent to calculating the Thevenin's resistance. Where they are dependent sources, the more general method must be used. That is, the voltage at the terminals is calculated for an injection of a 1 ampere test current at the terminals. This voltage divided by the 1 ampere current, that is 1 ampere current, is the Norton's impedance RNO. This method must be used if the circuit contains dependent sources, but it can be used in all cases, even when there are no dependent sources. Conclusion. It is a fact that Mayer was the first to publish the construction of a parallel form equivalent generator for a given linear network. Perhaps Mayer was inspired by the existence of Thevenin's series form equivalent generator. In the United States, the parallel form generator was independently contributed by E.L. Norton of Bell Telephone Laboratories. However, his theorem was formulated specifically for the time-free periodic steady state. So, it was not exactly the same as Mayer's theorem. The first statement of what later became Norton's theorem appeared in an unpublished BTL patent application data in November 3rd, 1926. This was the same month and year that Mayer's theorem was published. Thank you.